right, great. Hi, everybody. Welcome to the Spring 2022 Data Science Discovery Program Showcase. My name is Anthony Swin. I'm the director of the program. Maybe I'll give you a quick introduction about Discovery if you don't know about it already. The Data Science Discovery Program is really focused on two major items. First is advancing research and public good, both at UC Berkeley and beyond, whether it's government agencies, nonprofits, startups, and any organization that has a real compelling data science need. We also really are focused on providing long-term immersive student experiences that go beyond what a capstone does or beyond a project-based course. And we have many students that work on projects over several years. Oops. General logistics about the history of the Discovery Program. It started back in 2015, so we're celebrating almost exactly our 7th year. We have over 1,500 students that have been part of the program since the inception, and around 400 plus projects that have, across many domains, have been part of this initiative. This semester, we had over 200 students and over 60 projects that were part of the program. And we also were taking a leadership role in improving consultation support for research projects and adding additional computing resources. This is the team right now. It's a great team of graduate students and undergraduate program coordinators. And all the credit goes to them for making the program possible. Also want to shout out to partners on this initiative. BIDS, which is an organization that helped start this initiative back in 2015. D-Lab, which provided consulting support. Research IT provided kind of the Savio, computing resources for our students. Skydeck for partnering with various startups that they incubate, and Microsoft providing Azure cloud resources and other support. I now want to just allow Christina Teller, our Executive Director of the Data Science Undergraduate Studies Program, to say a few words. Christina.
Thanks, Anthony, and thanks for the kind of historical overview. I think it's really impressive just to understand the longevity of the program and the number of projects and volume of students who have been involved. So as Anthony said, I am Executive Director in Data Science Undergraduate Studies. I'm in my first year in the role and have been on campus for a long time. And just really happy to be here today. This is the Discovery project is just such an exciting example of just really the brilliance of the students throughout the data science ecosystem. And I think it's a really great example of the interdisciplinary approach, that students within the data science, within our ecosystem take, and just the incredible projects and thinking and research that our students are capable of, and appreciate everybody's hard work. Anthony has certainly led this program through it's been a very, very busy year. And so we definitely want to thank him and thank all the undergraduate participants and all of the graduate students for all of your support. And I will turn it back to Anthony.
Thank you, Christina. Oops, let me go to the next slide. Oops, oh, I skipped ahead a little bit. I want to now introduce, Alex, if you want to talk about the projects overall.
Yeah, and we've had an excellent year with Discovery, and we have a few excellent projects this semester that we're featuring today in the showcase, although you should keep an eye out on our website. Later on, we will feature even more projects who we couldn't fit in today. So hopefully we can send out that link to everyone later. But here are a few of the teams that will be presenting today. And each team will give about 7 minutes. This is the schedule, and I'll introduce each team in between. So, we see teams like BART, Catalyst Off-Grid Advisors, Sea Light Technologies. There are a bunch of excellent teams spanning all different fields, including science and technology, public transportation, geography, and social goods. So we're really excited to be able to hear from these teams today and see their great work this semester. And some teams have even been continuing for many semesters now. So without further ado, at the end, we'll do this awards ceremony. So, stay at the end after the last presentation, and we'll feature some of the teams that really shined this year with these topics. One thing that I did want to go over is this housekeeping slide. Because we're so tight on time today, we really encourage everyone to ask your questions in the chat, and the teams can then respond to those questions while the other teams are presenting, just so we can kind of keep things moving and be respectful of everyone's time today. The session is recorded. I think you'll all have already gotten a message about that, so just keep in mind that we are recording today. We're hoping all presentations can keep within 7 minutes. And like I mentioned earlier, additional project presentations will be posted on the website, so please look out for that. We have so many projects this semester. The program has grown really extensively, so unfortunately not everyone could be featured today, but that doesn't mean that these are the only projects that are really impactful. In fact, most of our projects have done really excellent work. So I think without further ado, I'm going to introduce the first team, which is the Bay Area Rapid Transit, or BART project, Insights from Data for Maintenance and Operational Excellence. So I think I've already given the individual sharing access for that. Hannah, are you ready?
Yes, I'll share right now. Thank you.
Excellent.
Okay. While Hannah is sharing, I guess I will be the one who has the pleasure of starting us off. So hello, my name is Aaron Lee, and I'll be presenting the first few slides of the BART project. So our project consists of mainly a one-screen visualization for the managers of BART to just be aware of the overall situations of operations with a single glance. So I guess I'll be detailing sort of the high-level view of everything, and we'll kind of be getting into the more finer grain details as we go throughout this presentation. So to start off, our visualization consists of two parts: a swim lane diagram and a map. So the swim lane diagram is essentially used to visualize each log based on category of the incident in chronological order. And our categories consist of medical, police, delays, mechanical, electrical, and other. These were hard-coded categories that were determined after using an unsupervised model, and which my colleague Jason will be detailing a little bit later. And through this visualization, we're able to see sort of the trends in category incidents throughout the time. And this visualization was done in Altair or Vega. So the next part of the visualization consists of a map. And on this map, we're able to quickly locate where incidents have occurred throughout BART's many stations. And we can also we can see the corresponding incident case on the swim lane chart. So the next part of the project is consisting of geomorphing the coordinates. So how exactly do we get the coordinates of non-consumer BART stations onto the map? So this was the project that I worked on. And some of the initial attempts that we used to try and solve this issue were to we had a system of geospatial non-consumer BART coordinates, and we wanted them to be laid out visually onto this map. And so the first attempt that we tried was linear regression. The next attempt we had tried was from computer vision using a homography matrix. But ultimately, we determined that using this technique of just using ratios with reference points was the best way to solve this issue. I won't go into too much of the details of how exactly this works, but it does consist of using ratios from consumer BART stations as reference points. And we were later able to add fixes depending on the use, such as jittering. And this is used for the later parts of the project, such as the visualization, but the visualization itself is still a work in progress. And now we'll move on to Hannah, who will be showing us a demo of this.
Hi everyone, I'm Hannah. I was the data visualizations lead for this semester. So I'll just be going over a demo. So here's our visualization just in the Jupyter notebook, so it's easier for you guys to see. Here's our geographical visualization side by side with our swim lane chart. So if we look at the swim lane chart, we see we have our categories for each of the incidents, and the icons used to display the incidents are related to the category as well. So we have delays, mechanical, and our other categories, and the x-axis is our timestamps. So all of these are in chronological order as well. So this visualization basically captures each instance relation with time and category. And then if we scroll over to our geographical visualization, we have the same icons related to categories, same as it was in our swim lane chart. And here they, along with Aaron's project of morphing the locations so that they're more realistic, we have all these incidents mapped onto the BART tracks. So we see where they are on the tracks. And also, if you hover over each icon for the swim lane chart, you can see the log entry, the location, and the time of the incident. And for the geographical visualization, we can see the station name and entry. And then to tie these two visualizations together, you can select one or multiple icons on either chart, as many as you want. And you can see them also in the other chart as well. So these are the same icons highlighted here. So you can just see an overall view of where they are on the track, the time of the incident, and type of incident, along with their descriptions. So this is just a big picture visualization so we can see more trends and insights. So now I will bring it back to our presentation and pass it on to Jason to explain the model of how we were able to categorize each incident.
All right, yep. So I'm Jason, and I will be explaining a general overview of our classification model. And as this project is a continuation of a previous semester's project, I would like to go over that model first. So that model essentially classified based on this concept of word embeddings, which we trained through a neural network. And a quick overview, you take an input sentence, and then for each word, you map it to its corresponding embedding, and then you take the average of those embeddings, and then you classify based off of that. So it was a very straightforward, simple feed-forward network that did surprisingly well for the task. You can, next slide, yeah. So some areas of improvement for that model. Our biggest challenge was obtaining the training data to train the model. And the reason for that is because we have to go through each log and manually classify it, which is difficult for us as the logs were not very intuitive to us, as they included a lot of acronyms and other codes. So we decided to explore some unsupervised learning techniques, such as clustering, autoencoders, and zero-shot classification. Some concepts I'll go more into detail into later on. And then our next area, no, wait, go back. Yeah, so another issue with the model was that because we simply took an average of the word embeddings, word context and position was not really taken into account. So we thought it'd be a good idea to look into other architectures, such as recurrent neural networks, convolutions, and transformers. And then our final issue was that because we were trained on using only labeled training data, or domain knowledge was very specific, and it could not really be applied to any other type of application. So our solution for that was we research different libraries and open source data sets. And I think a big one was to use a pre-trained model as a base, just for general information. Yeah. And so a little bit about zero-shot classification, which is the main concept that our model is based around. Essentially, the idea is that you have, you first define a set of labels that you would like to give, and each of the labels has a definition. And then essentially whenever you get a new entry, you compare the attributes of that object with the definitions of the labels and classify based off of that. So for example, here, like if you have a model that it's only been trained to recognize horses, it can still recognize a zebra if you tell it that a zebra looks like a striped horse. And an advantage for that is that it's it's a lot more general and applicable to more situations. And then the next, our main feature extraction feature is through autoencoders. And an autoencoder architecture consists of two parts, an encoder and a decoder. The encoder compresses an input object into some sort of numerical encoding, which is typically much smaller than the original input. And this is done to sort of force the encoder to isolate the most important parts of the input and the most important features. And then the decoder tries to reconstruct the original object from the encoding. And the way we train encoders is we first give it inputs that are, we damage a set of inputs and then feed the damaged inputs through the autoencoder and try to get the original undamaged input. And that really forces the encoder to basically select only the most important features. And then an important concept is that we only use the encoder after we're done training with it. All right, so then for a general.
Hey, Jason, you're a little bit over time right now, and we do have some teams that have a tight schedule. Sorry about that. If you do send us a video, we will feature it though on our website.
Thank you.
Thank you so much.
Yeah, thanks, guys. As I mentioned earlier, please post your questions in the chat. I'm sure the team would love to answer any questions regarding the things that they weren't able to cover as well. But in the interest of time, we do have to move on to the next team, which is the Catalyst Off-Grid Advisors team, expanding the Access and Stakes platform. So it seems like we're ready to go on that one.
Hi, my name is Ritika Surdana.
Hi, and I'm William Shu.
And today we'll be summarizing our project with Catalyst Off-Grid Advisors as part of Berkeley's Data Science Discovery Program. For context, Catalyst is a consultancy that's focused on solving the global energy access deficit within different countries in Africa. So in the past, Catalyst has worked with DSDP to develop an Access Insights platform, and William and I really helped develop that further through data cleaning, aggregation, and visualizations. The primary issue at hand is that Nigeria's economy is incredibly dependent on these small gasoline generators that have a collective capacity of 8 times more than Nigeria's entire national grid. And these generators are what is damaging for the environment, government, and the community as a whole. Our task this semester was to take raw data on current solar and storage systems in different regions in Nigeria and find patterns through data analysis that could uncover some deeper truths about what's actually happening on site. The ultimate goal was to support the Access to Energy Institute by having them use these trends to facilitate a better transition to more renewable energy sources and make more effective business decisions in the long run. Next, in terms of the actual data, we received multiple data sets on 82 total solar generators in Nigeria, which were labeled AAM systems by where they were provided from. Each system came with a unique ID, and it also came in 5-minute timestamps with a lot of different information that covered each system's latitude and longitude, temperature of the battery, temperature of the MPPT device, the city in which the panel is located, input and output voltages and currents, and more. Unfortunately, we did encounter some limitations. For example, 30 out of the 82 systems do not have latitude and longitude values. So I estimated geographic clusters based on some general locations of the cities. And William also dealt with a lot of null values and missing numbers for grid voltages, which again was tackled through a series of data cleaning and validation strategies, which we will be going over in more depth soon. And now our solution. So my part of the project was on the efficiency of AAM systems, and William worked more on blackouts. So I started off with considerable data exploration and cleaning to see what exactly was involved in the data. And I was provided with a very dense data set with a wide range of timestamps per day scattered through different panels. And in order to make valuable conclusions, I wanted to subset all of those AAMs with only those that had a threshold of 96% or more of expected timestamps between 6 a.m. and 6 p.m., which is what I constitute as a full day of power output through different analyses. So over here, we can see a distribution of what the expected numbers should be per AAM, and then we have the visualization of all AAMs compared to that. So using this clean data with the right number of days and timestamps, I was able to make some distributions on daily PV yields and average PV yields, as well as efficiencies. Once I had this data frame of good AAMs, I made some more in-depth analysis, such as a distribution of daily PV yields. I also found efficiency through comparing the theoretical yield versus the actual yield that we received from this data set. And I used the global solar atlas to find what the expected PV out value should be in a certain location in Nigeria. And I compared that with the AAM systems that were in that location to see how they compare with what it should be. And I graphed a distribution of those efficiencies. And we can see here that the average efficiency is 41.14%. The last thing I did was comparing the PV panel input to the MPPT output, which was an interesting observation that we found. And that is at the end of our notebook here. The orange line here represents that the PV panel input should be equal to the MPPT output, and all points should be below this orange line. However, we can see that a large number of data points are scattered above that line, which shows another difficulty in the data that was provided, which we will be working with in our next steps. So what I found through these reproducible functions where you can put in a start date and end date and see efficiencies, see distributions of yields, is that there's a lot of variation in performance of each AAM system, even within the same geographic cluster. So if you compare, we did some test analysis comparing AAM 257 and 273, and some have double the amount of wattage in power output than others, and we're not sure why those factors are. So a lot of panels in general are not producing as much electricity as one would hope given the global solar atlas estimates. And the size of the disparity probably means that both installation and maintenance, as well as cleaning, needs to be better examined. So our next steps would be to organize the data by geographic cluster and over time. For example, in a region like Ekin, what is the daily average per month for each AAM? And then some future recommendations that we have based on this analysis to figure out how many solar owners you could reach out to in a given month, and then run a report highlighting the AAMs with the least yields compared to neighboring AAMs in that same area, and keep following up with those owners to see how we could better support microenterprises.
All right. Thank you so much, Ritika. I'll be moving on to my portion of the project, which focuses on the connection between these solar generators and Nigeria's national power grid. So this is a diagram of what each AAM system looks like. Ritika just walked through her investigation on the efficiency dealing with multiple variables like input voltage, output voltage, temperature. But I'm focused on this external supply over here. This is the juice that gets pulled from Nigeria's national power grid. And in an ideal situation, if external supply is working correctly, the voltage will just follow this purple line, and it won't require the use of solar panel generators at all. However, Nigeria's national grid is very inconsistent. There's frequent outages, there's frequent blackouts, and survey data reveals that in some parts of Nigeria, citizens can go days without power, and they may only get electricity like on average a few hours a day. And this is why there's such heavy reliance on these AAM systems, these solar generators. So our overall goal is like when national grid is on, our load simply uses the external supply, and only when there's like a blackout or a disconnect, then the solar panel is used to generate electricity. So it's very important to get data on blackouts. I wanted to make a methodology that would gather summary statistics on these blackouts and ultimately predict when these blackouts happen. This is essentially what an AAM looks like when we isolate it. It's a plot here of grid voltage over a 48-hour period. And you can see that the grid voltage mostly hovers roughly around 240 volts, which is good. This is what we want, because standard appliances generally run on either 220 to 240 voltage. And so this means that 240 volts is the right amount to meet industry standards. But you'll also notice that frequently the voltage drops down to 0 volts inexplicably. So like for this 12-hour chunk of time and from smaller time frames, the grid voltage is at 0 volts. And this means there was a blackout. We don't want that. So our goal is to find overarching blackout statistics. And so the way we did that, first, I'll go over this map to share my methodology. Here's a map of Nigeria with all 177 AAM systems that I used in my data collection. And let's zoom into just these two. These are two completely separate generators. So we can say that one of them is owned by like a hairdresser company, and the other is like a residential home, and their AAM system private. They're run completely separately from each other. So the idea is that it's very possible that one AAM system owner could disconnect their AAM from the grid and notice a drop down to 0 volts. But if we observe multiple AAM systems that are nearby each other, meaning that they run on the same part of the national grid, and they both drop down to 0 volts at the same time frame, this is very unlikely to be a coincidence, and it means that there was almost certainly a blackout. So putting this into code, what we wanted to do is look at AAMs that are geographically next to each other. And this leads into clustering. So we used k-means clustering to bring the AAMs and give them each a label. So for example, AAM 223 was given cluster label 4. Here's a mapping of what each cluster looks like. You'll notice it looks very similar to the overall distribution of AAM systems in Nigeria. That's because it basically is the same graph, it's latitude and longitude. And so that's finding local data, hyperlocal data. My second goal is to find quality data, basically data cleaning. And so I ran this code, and it maps all 177 AAM systems over time. Some of this data is good. This is like the distribution that we want to see, but you'll notice that a lot of this data is not very clean. There's like big gaps, like in this one over here, where there's just 0 voltage for a very long time. There's NAN values, like in grid voltage for AAM system 272, there's so much 0 data. So that's finding quality AAM systems. And I just went through all 177 and I manually selected which AAMs I thought gave good data. So this leads into the final part of my project, identifying blackouts given the quality hyperlocal AAMs. We don't have time to go into how I developed the algorithm, but some highlights is that I start with developing a binary tracker. I do some group bys, some tests, and then I press the data frame. But I'll go over more into this in like a blog post. But for now, the end result is that I created a reproducible function where you can input the two AAMs that you want, a start time and an end time, and it'll output some summary statistic graphs and how many blackouts that they observed in that time frame, and then the mean, median, and max blackout time. All right. One last share screen. Okay. So finally, we'll move on to the impacts of our project. First off, we discovered that Nigeria's national grid is extremely inconsistent. With inefficiencies in certain AAM systems and blackouts in the national grid, the current systems are unable to support families and micro enterprises in Nigeria. We sincerely hope the work we did will help A2EI predict national grid blackout statistics and increase the efficiency of their AAM systems. And in the longer term, this institute can reach out to potential customers where the panels aren't producing the efficiency they're looking for and troubleshoot. And finally, next steps for our project. We plan to research some of the circumstantial factors, such as precipitation or dust on solar panels that cause these lower efficiencies. And we want to utilize GIS to map grid uptime by location.
And that's it for our presentation today. Thank you so much. Let us know if you have any questions.
Hello, everyone. This is Elizabeth, Maggie, and Bihan, and we've been working with the American Heart Association on the Get With The Guidelines registry in the Data Science Discovery Program. Today, we'll be presenting on the work we have done over the course of the semester. Next slide, please. So the obvious challenge, cardiovascular disease is one of the greatest challenges in the medical field. It is the current #1 cause of death, and every 2 seconds, someone around the world dies from cardiovascular disease, and 70.5 million deaths occur each year around the world. It is also a very costly disease, as you can see from the stats here. Next slide, please. So the mission statement of the American Heart Association is to be a relentless force for a world of longer and healthier lives. Next slide, please. The general workflow works kind of like this. The AHA writes the guidelines for the clinicians on how to care for patients with cardiovascular disease and stroke. The data for these guidelines come from hospitals all across the US that work with the AHA and collect data from registries. These data are then delivered into a secure workspace and published on the precision medicine platform for other academics to conduct research. Our work as an intern at AHA includes cleaning up and preparing the data sets from the registries to be delivered in the workspace. Since we've been working on different registries, I'll first present my work and then Maggie and Bihan will present theirs. Next slide, please. The registry data I've been working on is the resuscitation registry data. It consists of patients that have experienced an in-hospital resuscitation event or received post-cardiac arrest care following an in-hospital or out-of-hospital event. There are 12 different data sets that captures like different aspects, including cardiopulmonary arrest, medical emergency team, and acute respiratory compromise, which is the one I've been working on to clean up for the most part using our studio. And next slide, please. The ARC event dataset has around 74,000 observations and around 285 variables. Some of the variables include binary ones, such as interventions already in place, multi-select variables, such as pre-existing conditions. In that case, we need to split them into several different variables, and also event date, time, location variables, and age variables, which are a bit harder to clean up since they come with a precision variable and different medical procedures have different demands for precision of date and time. In this case, it is important to implement checks on whether the precision variables match the actual date and time and clean up the ones that do not match. I'll then pass on to Maggie to talk about her work.
Hello, my name is Maggie. I've been working on with the deadline to have a registry platform with the data science team at AHA. The data for this guideline come from the hospital all across the US that work with the AHA we collect data in hospital through registries and data from the patient that have experience and in hospital and out of hospital CAT event. Then we clean, harmonize, and standardize the data and deliver it to our workspace. Next, please. For more detail, I designed the database system for AHA precision medicine platform for the CAT with the backend team using the Django framework in Python and with Hitachi and AWS to deliver a secure and maintainable platform. The image on the left side shows some fraction of the coding setup demo for the database system. The image on the middle and the right shows the user can request a workspace with tool, including Python, SQL queries, and Jupyter Notebook to host their code and manage their project, whether they're working with the team or on their own. Next, please. And I will give in to Wahan to introduce more about the AFib Park.
Good afternoon, everyone. I'll be talking more about the AFib registry, and that's most of the work that I did over the past semester. So as you guys know, atrial fibrillation is a common arrhythmia, and it accounts for more than 450,000 hospitalizations each year in the United States. That's an insane amount of people. That's a big amount of people that are getting hospitalized, and I think American Heart Association's the main reason for this program is it's designed to assist hospitals, hospital care teams in consistently providing the latest evidence-based treatment for their AFib patients. At the same time, it offers a means of monitoring the quality of AFib care in US hospitals and building a database for continued research and further quality improvement. The work we did over the past semester, it has impacted more than 159 hospitals and around 76,530 patients. In the semester, I started with learning about Django, and my main work was in creating the backend database for the Get With Guidelines registry. As you can see on the left, the leftmost image is one of the few tables that I created. It is just one of the many tables that we had to create. In the middle, you see how this the code that we did on the left ties into the entire database, and we created a bunch of tables for our particular registry. So you can see for AFib, the AFib demographics table looks something like the picture on the right. Our job was to just our first task was to create a lot of tables and make sure that all the fields and all the forms that come through for the AFib patients are covered. Our next part was creating scripts, and these scripts were written in Python and the main part was to make sure that that we were importing and exporting our CSV files correctly. I think that was one of the most important tasks in our work, because we had to make sure that the tables that we did create were all done so really well, and like they were free of any bugs. I think we can also this is more of we can also provide more of an overview of what we did and how this registry databases can be used. They can be used in certain publications, and a lot of publications have already been published using these registry databases. So to talk more about the impacts and publications, I'll pass it on to Maggie for the next slide.
Hey guys, I just want to let you know you're kind of over time. So if you guys could try and wrap it up a little bit, maybe one summary slide. We have to move on to the next team. We do have some time restrictions today.
Yes, sure. I'll just briefly talk about the publication. I think that's the most valuable of the AHA, giving the value to the global researcher. So the overall, the AHA precision medicine platform workspace enable researcher to work collaboratively and securely with our dataset platform tool to accelerate their discovery and improve the quality of cardiovascular and stroke care. And this is a little one of the example that's our CAD and the EFIT database help the global researcher to do their research topic.
Yes, as Maggie said, this is our last slide. This was a brief overview of the learnings and conclusions we also had apart from the publication. So we worked with big data and we got to know the ins and outs of a data science lifecycle, especially cleaning, loading, and visualizing data. We created big databases that impacts tens and thousands of lives. And we also wrote like clean, efficient code, and we also learned how to test the code. Throughout the semester, it was a really fruitful semester, and we would like to thank EHA for providing us the opportunity. Our wonderful mentors are also here in the meeting supporting us. So big thank you for them, and big thank you to the Data Science Discovery Program for helping us with this.
Awesome. Thanks, guys. Really impressive work from all the teams so far. We're moving on now to C-like technologies, utilizing deep neural networks for object detections in retinal imaging data. And like I said, please try and keep it to 7 minutes, guys. We have so many great teams today. I wish we had enough time to go into all of the detail about your project, but unfortunately, we're a little bit tight. So try and keep it to 7 minutes if you can.
All right, can we start now? Hi, everyone. Here's our final presentations for Spring 2022 Data Discovery Project in collaboration with C-like Technologies on topic of utilizing deep neural network for object detections on slow retinal imaging data and a video sequence embedding to predict disease severity and recovery progress. Next slide, please. Here's a snapshot of our team.
Hi, everyone. My name is Jay. I'm a CS student here at UC Berkeley, class of 2024. In this project, I'm mainly working on data processing, engineering, object tracking. My interests include early disease detection and also reinforcement learning.
My name is Yifan Zhang, also sophomore studying computer science and statistics. I mainly focus on the pipeline implementation, data augmentation, modeling. My research interests are computer vision and reinforcement learning.
Hi guys, this is Joe. Nice meeting you all. I'm actually responsible for all data science and the AI related work and C-like technology, which is a Berkeley spin-off startup. It was great working with Yifan and Jay in this semester on this project. If you have any question on our work, our company, feel free to ask us. Thanks a lot.
Our motivation lies in early disease prediction based on retinal imaging. Retinal motions has been known as a strong biomarker for neurodegenerations. Thus, establishing a retinal coding of disease can be of great importance. For the past decades, feature engineering has been a manually exhaustive design and implemented process for many retinal-related studies. In this project, we wish to present a novel method to automatically learn the data representation of slow imaging data utilizing an end-to-end deep neural network-based approach. Particularly, we wish to focus on multiple sclerosis, a disease that affecting roughly 1 million patients within the United States. Here, I would like to introduce this concept of retinal encoding through the image embedding technologies or lower dimensional representation of images. It has been widely used in use cases such as image search. In this demo, we can see that if we search a car with specific type and make in a large database, the similar vehicles will pop up as they share similar embedding vectors. Using the same principle, we're able to train a deep neural network to understand the data and generate image embedding vectors to improve C-like Technologies' disease prediction system.
This is a demonstration of our model structure. As you can see, starting from the left, the slow image will directly fed into the DNN model, yielding different types of predictions, such as classification types, location of bounding boxes, geometric shapes of the object, as well as the feature points. Our training data consists of 206 images, randomly sampled from 327 GB of videos. All training images were resized to a constant frame size when fed into DNN. We focus on detecting 3 classes of objects on retinal images, as shown on the figure on the right, which depicts an instance of vessel crossings in red, fovea in blue, and tumbling in green. The figure on the left is the total number of instances in our training dataset.
One limitation we face in this project is that we only have 306 images annotated, which is not ideal or enough to train a deep neural network. To boost our training data, we decided to generate new synthetic images through data augmentations. As you can see on the right, we have generated multiple copies based on the same original training image using various methods such as random brightness contrast and horizontal flip. Utilizing all these methods, we now have a training set of size 1176. Next slide, please. Here are the results of our training. The diagram on the left shows the metrics of precision with recall, while the pictures on the right shows actual detections made by the deep neural network on the actual images. We used a deep neural network-based model, ULV5, for object detections with a hyperparameter of batch size of 16, image size of 832, epochs 100. We achieved a MAP, or mean average precision, of 0.569 for vessel crossing detections.
In conclusion, we observe clustering behavior of image embedding vectors correlates to the higher confidence detection of patients' retinal subtleties. With those correlations, we are able to detect and predict different types of landmarks by extracting latent features of slow video data using DNN models. Our model can capture the subtle differences in those raw slow images and predict diseases based on that. In future work, we plan to deploy a data-centric approach to improve the quality of training data. The figure on the left displays the pixel intensity of 2 vessel crossings, each of which has 2 peaks representing the darker center and the lighter edge points of a vessel crossing. By comparing the ratio of those 2 peaks, we are able to define a fixed metric to filter out the bad quality data to improve our model accuracy. We will also test different detection models such as ULOX and EfficientNet. Eventually, we'll build a recurrent neural network model to learn the temporal correlations.
Excellent. Great work, guys. I think we're going to move on to the next team, Cortec. And the title of the project is Project AIE. So Kai, if you're ready to present, feel free to share your screen.
Yeah, I'll dive right into it. All right. Okay, so we are Project AEI, and this is our 4th semester here at Cal. I'm also a Cal student, and I'm a startup founder as well. Started a company called Core AI that is building a lot of the cool stuff you're going to see here. So yeah, we started this project with 2 goals, and originally, we have the original name of this project, which was using AI and real-time data for the development of an early warning system for public safety and the recognition of emotions. Obviously, not a very marketable name for research project, so we had to cut that down. But yeah, so we have, our main goal is to use emotion recognition software to both predict, I guess, emotional states, and also predict physical violence before it happens, and then also, recommend mindfulness content to users in real time based on their emotional states as well. And so in terms of our research question, it was, can we actually do the things that we're talking about? Can we predict physical violence based on emotions? Can we recommend content to users to meet their emotional needs in real time? And so the answer to that question is about 10 slides later. But yeah, so in terms of our data to, data that we used to actually build the model, it came from, university data sets like TESS and SAVI and RobDes, which are common across the, voice biomarker, bioacoustic emotion recognition space. And then also, in terms of our behavior prediction system, which, we're incorporating a larger span of sounds, being gunshot sounds, explosions, screams, and the like. We parse through Google Audio Set to source those sounds as well. And so in terms of our data augmentation techniques, because again, we are using, or as I'll describe later, we're using a convolutional neural network to accomplish this. For our data augmentation, we pumped in some white Gaussian noise, used some pitch shift, augmented these with these kind of augmentations. We've reduced, from 10,000 original raw samples to about 40,000 samples. And then in terms of the input that the model takes in, we have, it takes in Mel spectrograms. We're also feature selecting for, zero crossing rate, and then RMSE, which, RMSE is the energy of a sound. So kind of, I guess, how much punch it has. And then zero crossing rate is the rate of sign change for a signal. So here's our model. We have a neural network with 3 parallel layers, a 2D CNN layer, a 1D CNN layer, and a transformer encoder layer. And so, this, on our training and test accuracy, or for validation accuracy here, we have 75% in terms of our accuracy. And then, just to kind of have a base rating for how that performs as far as an actual person in the crowd. The average person has about 63% accuracy when recognizing emotions in other people. So, this is kind of the industry standard right now for, neural nets that are capable of recognizing emotions in this particular way. And so here's our model performance. Again, kind of asymptotically approaching, 75% for validation. Training accuracy was, near 100%. And then here's a graph of our, our loss functions as well. And so why were we doing this, right? Why are we building these models? So we wanted to shoehorn the model into our emotion recognition model into a mindfulness app that could recognize, how you're feeling from the sound of your voice, and then recommend mindfulness content to you in real time. And so what we then be doing with that information from your emotions is, pulling from our content library of 1,000 mindfulness practices written by, world experts at Berkeley, Stanford, and Harvard, and then directing you to, the content that we feel, or an assortment of content that we feel is, best for this particular emotional need. And so this app will be coming out, hopefully September in the fall semester. And then we're going to be launching kind of a beta for, our closed beta this summer for developers and, special people, I suppose. But yeah, so here's the app recording process, right? So you open it up, you hit record, you tell us about your day, say anything you want. It loads for a second, and then boom, we've got, emotion classification. And then here are some recommendations and, tiles that we'll show you thereafter. But if we feel like, oh man, that's how I'm feeling, because again, 75%, not 100%, and honestly, a person wouldn't be able to recommend or recognize your emotions 100% of the time accurately. So if you feel like we've misrepresented how you're feeling, you have the option to kind of self-select and receive recommendations that are better suited to your, personalized emotional needs going forward. And so in terms of the practices, I said that they came from these industry experts at Berkeley, Stanford, and Harvard. And so in addition to those, we also have stuff from the Greater Good Science Center, as they are one of our partners. And, one of my good friends is, Professor Dr. Keltner out here. And so for the past 2 years, we've really been working very closely with him and the Greater Good Science Center as well. And so we've also, the next logical step for building an algorithm that's, going to be good and, built by and backed by a bunch of, cool, awesome people and world-class people in the field, is to kind of extend over an API as time goes on. And so what we did was we built an API, and over the course of this semester, to kind of allow corporations to be able to use our models to make emotional predictions in real time, and also, built up this client side and made some improvements over the course of this semester. We had talked a little bit about this last semester and kind of introduced it, but we're mostly, as far as the API design and development, it's been fine tuning for this spring semester. And so in terms of the implementation of like how it works, we have, it takes in a WAV file. It converts that that WAV file into a spectrogram, and the necessary tensors that it needs to be able to, pass into the model. And then we, run the predict function. It's as simple as that. So yeah, and so here's a new thing for our behavior prediction stuff. So we have, over the course of this next semester here, we kind of started this in terms of some planning and some UI design. We're building a behavior prediction system called Arkham. And so what this is going to be is, a new form of body camera that can, kind of do scene analysis as far as, the acoustic and visual scenes in a given environment, and predict the likelihood of violence in that area at that time, hopefully in real time as well. But yeah, so you'll get to see some kind of, cool demonstrations of that, hopefully with the, the UI and the device paired together, as is the plan for next year sometime. But yeah, so we'll be prototyping that over the course of the next, 6 months or so, and you'll get to see it when it comes out. And so in terms of answers to our research questions of, can we actually produce or predict, violence before it happens. In terms of our exploratory data analysis from, I think about a year and a half ago, yes, we can correlate acoustic features with, instances of physical violence. And, does this extend beyond, in terms of our emotion predictions, beyond, I don't know, the typical standard of valence and arousal? Yeah, 100%. Because, Professor Keltner's on the team. He's not a very big fan of that. And he's written a lot of papers also to say that that's kind of a more, erroneous notion of, discerning emotions in terms of its actual, nuance. So, you can't exactly capture, I guess, the true depth and scale of emotions and, in a bipolar scale that's, kind of from, let's say, I'm speaking hypothetically here, but -5 to 5 and, 0 as your neutrality metric. So overwhelmingly, the answer to our question was, yes, we can do this. Yes, we can recommend mindfulness content to users based on their emotional states. And yes, we can predict physical behaviors before they occur using these emotional states as well. And so in summary, we have, the couple things that we worked on. We have the spectral analysis that we did for, kind of pre-processing our data. We built our, transformer models for, the actual AI model that I just described. We designed and, mostly built an app that will be launching next fall. We created an API and we fine-tuned it on the client side. And then we're also not listed here. They're going to be developing, Arkham for the fall and for the spring as well. And so here are some student contributions. And so just to kind of show you what the app actually looks like so far.
Kai, I don't know if we have time for the demo, but can you post it in the chat so people can watch it after?
Gotcha.
Sorry to cut you off. We have a team that has a tight time restriction right after you. So I just want to make sure that we get to everyone, but I would encourage everyone to watch this demo in the chat. And I think, thanks so much, Kai. I think we have to move on to the next team now.
Yeah, thanks for having me, guys.
Great. The next team is the People Lab, tackling mass incarceration through AB 2942, expediting case review summary for criminal case resentencing. Are you guys ready to share?
All right, can everyone? Okay. Yeah, Richard. Okay, cool. Okay, hi everyone. This is our project. It was called Tackling Mass Incarceration through AB 2942, expediting case review summary for criminal case resentencing. Okay, yeah, my name is Vivian.
I'm Chloe.
I'm Lydia.
And I'm Aileen.
And below is our project advisor, Jesse, who is also on this call. Could you click the next? Okay, yeah. So yeah, for today, we'll just talk about the background of this project, a piece of legislation that prompted it, as well as the problem of mass incarceration more broadly, and then the specifics of our project. Yeah, so just for some background about the bill that inspired this project, it's called AB 2942, which is a California bill that was passed a few years ago. And basically what the bill does is it allows prosecutors to go back and look at previous sentences of currently incarcerated people. And if it's not in the interest of justice to maintain that sentence, especially because of a long history of harsh sentencing laws, then the said prosecutor can resentence someone and decrease the time that they are incarcerated.
Yeah, so our project is against a larger backdrop of mass incarceration in the United States, and so we'll be going over just the main general aspect of mass incarceration. So first the big picture, then policies and some disparities that are in the criminal justice system. So first, the big picture. So again, the United States incarcerates more people than any other country in the world, and we spend billions of dollars on maintaining the criminal justice system each year. And we should care because millions of people are affected and harmed by this system, be it they themselves are currently incarcerated or formerly incarcerated or have a family member who has been impacted by incarceration. So how did we get here? Many people point to the war on drugs as sort of a catalyst that initialized our current state of mass incarceration. And this began in the 1970s as a crusade that essentially criminalized poverty and then by default criminalize Black and Brown Americans. And this was largely done through legislation, such as the Comprehensive Crime Control and Safe Streets Act and the Anti-Drug Abuse Act, which lengthened and made sentences more harsh for nonviolent drug crimes. And it's really difficult to talk about mass incarceration and the criminal justice system in the United States without talking about race. So despite making up only 12% of US residents, Black Americans represent 38% of the incarcerated population. And we got here because low-income communities of color are imprisoned at much higher rates, and they were impacted disproportionately by the policies from the war on drugs previously discussed. So now that we know a little bit about the problem and the background of the bill, we'll walk you through our project. First, we'll talk about our goals, what did we want to achieve, and what makes our project different. Then we'll talk about our data, our code, and what we did well and what can be improved on in the future.
All right, so with our project, our goal was to create a proof of concept for a tool that district attorneys can use to expedite the resentencing process. And so currently, for each eligible individual, it takes around 8 hours to manually assemble a case summary file for resentencing. And this makes the process of using AB 2942 super slow, inefficient, and ultimately it delays justice for incarcerated people. Our goal with this project is to use data science to be able to automate this process and help prosecutors by extracting the necessary information needed for the resentencing process. Moving on, we do want to stress that our project does not intend to create an algorithm to predict certain risk factors, such as an individual's risk of rehabilitation or recidivism. For example, a common use of algorithms in the justice system is to determine the risk assessment scores of incarcerated people, a popular algorithm for this being called COMPASS. And while COMPASS does increase efficiency, research shows that it is still largely biased in its scoring system. As you can see on the figure on the right, Black individuals were still twice as likely to be misclassified as high risk than their white counterparts. So to clarify, our project does not aim to create any sort of algorithm, but rather we want to use data science to create an efficient extraction and summarization tool that would bolster the use of anti-mass incarceration legislation. So next, we'll be giving an overview of the data that we worked off of. And unfortunately, due to confidentiality agreements, we can't show any of the actual work, but our team in partnership with For the People was given access to the files of 9 individuals by the California Department of Corrections and Rehabilitation. And they came in PDF form originally in 2 different types. So first we have the SOMS, the Strategic Offender Management System, and you can kind of see a mock example of that in the bottom right corner. And we also had the ERMS, the Electronic Records Management System, which were scanned documents that had a little bit more variation, and there were over 1,000 pages per individual.
Yeah, so now we'll go over the main aspects of the data that we were focusing on. So my aspect of the data was programming and education. This information is really essential for determining if an individual is eligible for resentencing, because it gives us an idea of what that individual is doing while they are incarcerated. So this includes information about self-help groups like Narcotics Anonymous and Alcoholics Anonymous, as well as education like a GED and adult education certificates.
I focused on analyzing rule violation reports, which is another component of the case review summary. And it basically just includes information about alleged rule violations while incarcerated, including the date, the type of violation, and any related follow-up documents like hearings about the allegation.
I worked on the individual history of incarcerated people, and this includes prior convictions, substance use history, gang affiliation, employment history prior to their prison time, and all of these factors all contribute to the determination of their classification scores, which I also worked to extract. And I focused on Chronos and work supervisors reports. So Chronos consisted of more detailed updates about programming and alleged violations. And work supervisors reports specifically consisted of details about a specific job worked, including pay and performance. And so next I'll give an overview of our coding process. So we started off by focusing.
I think you're going just a little bit over. I just want to let you know you have about 1 minute left. So if you could sum it up in 1 minute.
Okay, Thank you. Yeah, so first we focused on one individual's PDF file to locate relevant pages and information to extract. And then we found Python libraries and tools to help us convert information into a code-friendly form. Then we extracted data by writing functions and code to loop through the data, find relevant text, and clean up our data. And lastly, we generalized our code onto other files and increased our accuracy.
And in terms of what we did successfully, we were able to build functions and code that would extract information, whether it be the date of a violation or transferring a table in a PDF into a pandas data frame. And so on the whole, we did a pretty good job with that. In the long term, we want to test our code on a larger scale since we only have 9 files. And we also want to be able to generalize it to a broader variety of data and eventually consolidate each of the 4 components we worked on into one unified tool to create case review summaries. So yeah, that's our project. Thank you for listening. And we hope this is part of creating a better process for resentencing in the justice system.
Awesome, thanks so much. I do see you guys have a question in the chat, so feel free to answer that question also in the chat as we move on to our next theme, just in the interest of time, climate informatics, application for data science for localized climate prediction product. Is the person for this team ready to share? All right, go ahead, and do you have sharing access? Did you message me for that?
I have sharing access, so should I just share my screen?
Yeah, of course. Go ahead and get started. And just as a reminder, we do want to keep make sure we get to everyone. So please limit your presentations to 7 minutes. I'm just going to have to keep cutting you off, and I want to make sure we get to all of your wonderful work today.
Okay, so our project is data science for solar forecasting. And the client that we worked with is Informatics, which is a woman-owned company, and these two are our project leads, and they're also both co-founders. And here are the interns. I'm Jessica.
And I'm Manas. The other interns couldn't make it today, but both of us will be presenting the scope of what we did this semester.
Yeah, so what we worked on as interns, we did some data analysis, and then we were also able to do some market research. And then some of the tools that we used included IBM Cloud Computing, Python, and Jupyter Notebooks. And so the problem that we were trying to address was why we need solar forecasting. Climate change is increasing energy demand, and we wanted to be able to maximize the production of solar energy. So our first assignment was short-term solar forecasting. The things that we did for this part of the assignment was we collected the data for 10 different sites in the US, and then we also cleaned the data and padded missing values. And then lastly, we visualized and interpreted the data. So some of our preliminary results look like these. On the left, we see a basic plot of the diurnal cycle. And then on the right, we see a mean diurnal cycle of the observational data and also the forecasted, different types of forecasted data. And then another thing that we did was plotting the histograms of each of the GHI values at different hours of the day. And this is an example of one of the histograms that we were able to plot. And as we can see that there's a bimodal distribution here. So this strongly suggests that there is an overcast and sunny weather during the month of January in Hanford. And to compute the cloudy days, we found the mean of the GHI values in the month. And then we also compared each value with the mean. And if it was less than the mean, then it's considered a cloudy day. And we also calculated the root mean squared error values. This was just to see which of the forecasted data was more accurate compared to the observational data. And from this function right here that we coded out, we can see that the GFS model has the lowest difference when compared to the true observations. So that model was intended to be more accurate.
Yeah, okay, so after that, our next assignment was to conduct long-term solar forecasting. So if we go to the next slide. Basically what this was we extended a lot of the practices that we used for the short-term forecasting just to predict long-term analytics. So for short-term forecasting, we were predicting the next day's data, whereas for long-term, we were predicting maybe the next month or the next year. And in order to accomplish this, we collected and analyzed multiple years data from the Solar Forecast Arbiter platform. So here are some of the visualizations that we produced in this assignment. As you can see, they mirror some of the ones that were shown earlier. So the one on the left are plots of the hourly, daily, and monthly GHI values. Just for context, GHI is basically a measure of how sunny it is in that location. And on the right, we can see GHI values for each month. So we can kind of see the distribution in these histograms with the GHI values on the bottom. Okay, and then on the left over here, we use kind of that long-term data to create the diurnal cycle for the locations. So these are the GHI values over here. So we can see Seattle is in green, and on average, that's a lower GHI value per day when compared to a location like Hawaii, which makes sense. And on the right, we calculated the annual climatology for each location, so showing the GHI distribution throughout the year. So there's an example from Sterling, Virginia. Okay, and then we don't have time to show every single location, but we compiled basically all of our findings for the mean GHI for each month in kind of like in a data frame. So that would provide insights into the climate patterns for each location that we looked into. All right, so after that, the next part of our assignment was to build machine learning models for short and long-term solar forecasting. So the way we did this is we used IBM Watson Studio, specifically the Auto AI feature, to train and deliver two types of machine learning solar forecasting models. The first is for short-term solar forecasting to predict a day ahead, and the next is long-term to predict a year ahead. The reason for this is Informatics is trying to create a product that can help businesses predict future climate patterns, and having machine learning models would really help with that product. So this is kind of what the Auto AI looks like. Basically what you do is you feed in your observation data. So for the short-term forecasting, it would be hourly. For long-term, it would be monthly. And then we put this into the system and it produced the top 3 models or pipelines that would be able to predict the data best. What we did from there is we actually create a runtime of each of those models and try to see which model is actually the most accurate based off the observation data we have. So you can kind of see that over here. We create a runtime for each of the top 3 machine learning algorithms for each location, and we just tried to determine accuracy based off of inspection. So here's an example of what that looks like. On the left, we have the yearly climatology for Salt Lake City. And on the right, we have 2 of the models that are produced by the Auto AI. The top one is a linear regression model. As you can see, it's not really that great of a fit because it has a lot of ups and downs. That doesn't really mirror what's happening on the left in the climatology. And the maximums don't really match up, since the maximum on the left is around 325, and on the right, it is around 300. Whereas the model on the bottom is a much better fit, having maximums that match up and also mirroring much of the shape of the climatology on the left. So that's kind of the process we used for all the locations we looked at.
Okay, and then while we did all of this data analysis, we also wanted to be able to understand the market and also the pain points of the solar utility companies. And so we studied the media literature and also conducted interviews with solar utility providers. So 2 of the interviews that we had was with KIUC, they're from Hawaii, and SJCE, located in California. In Hawaii, we found out that they experience more hurricanes and floods rather than wildfires and heat waves. And they are actually operating with 65 to 70% renewable energy. So this is a mix of solar, hydro, and biomass. And so their biggest concern was actually the impact of hydro production rather than solar energy production. Whereas in California, they experience a lot of wildfires, which reduce the amount of solar energy produced. And heat waves also drive up the electricity usage and can cause the grid to overload. And so for them, having an accurate solar forecasting would actually help them save money because they can buy electricity differently ahead of time. So that was a basic summary of what we worked on over the course of the semester with Climaformatics, and thank you for listening.
Great, thank you guys. I'm going to keep an eye out for questions in the chat. I don't see any right now, but let's move on to the next team. This team's from the Department of Geography. How does a public regional eco-literacy initiative change the environmental and sustainability education at schools? Is that team ready to share? Great.
Great, so we'll be presenting our discovery project, Understanding Environmental Awareness in Schools. Our team lead was Nama Sadan, and then I'll let the team introduce themselves.
Hi, I'm Aisha.
Hello, I'm Joe.
I'm Rohan.
My name is Salvador.
I'm Alina Drue.
Great, so I'll get us started with a little bit of the background to the project. So we focus on environmental education, and really the purpose of that is to build awareness, exposure, and an ability to act, especially in students in the K through 12 system going through all kinds of schools. And so the problem that we noticed was that there's different environmental education access that different schools have, as well as different kinds of environmental education. And so each school in each district might have a different form of that. And so a possible solution was San Mateo County's Public Regional Ecoliteracy Initiative, which attempts to coordinate in such a way so that schools receive both equal access and equal diversity of education. So our focus, our question is, how does a Public Regional Ecoliteracy Initiative change the environmental and sustainability education in schools? And as I mentioned, our two aspects are the access, so the schools' ability to receive this education, as well as the diversity of the services that school access. Great. So our data set, right, thank you. So the method that we use is social network analysis. And what social network analysis does is measure the relationships between different sets of actors. In our project, the actors are schools as well as environmental education organizations, and we seek to understand the connection between these two. So our data set consisted of a survey of 171 schools, as well as 13 environmental education organizations over the 6-year period, 2015 to 2021. Great, and our final result was an edges data set with 1,283 edges, where an edge represents a connection between a school and an environmental education organization. Now we'll move on to the access part.
Yeah, so as we defined earlier, the access is the distribution of environmental education services to various schools. In order to sort of view this in plots, we use a tool called Kumu. And so that plot that you could see over there, essentially it's a tool that allows you to examine network analysis or to examine the connections between multiple different types of organizations. So for example, in this plot, this yellow circle consists of the various organizations present in our data set, and the blue circles around them represent all the schools. And so each connection between the organization and the school means that that organization serves that school, and the width of each connection represents how many students are served in that organization school pair. There are buttons on the top of the graph that highlight one connection. These are the schools with 1 or 2 connections, and then these are the schools with more than 2 connections, so basically all of them.
And here we look at absolute access. So we define absolute access as whether a school has any access to ESC services. So it either is connected or it doesn't. It doesn't exactly matter how many providers a school has, but just if it has any providers or not. So what does it really mean for a school to have multiple connections? That means that a school can be connected to multiple ESC providers. So for example, a school can have 2 connections if it may be connected to an outdoor education provider and a wasteland management education provider. So here we see that the number of connected schools is pretty consistent over time, slightly increasing.
In the realm of access, we also looked at the correlation between the number of connections the school has and the free and reduced lunch or reduced lunch rate of the school. And we wanted to see if that correlation or that association changed over the years in which we had data on. And in the plots here, we can see that at first, the correlation is negative as free and reduced lunch rate increases. And then after it goes over the mean, the correlation is positive, meaning that the higher free and reduced lunch rate in a school, the more connections that school has. So what this means is that schools that are more affluent, meaning schools that have a lower free and reduced lunch rate, and schools that are less affluent, meaning schools that have a high free reduced lunch rate, are more likely to have a higher number of connections in San Mateo County, whereas schools that have a rather average free reduced lunch rate do not have as many connections. Another thing we looked at was ESTF, which is basically a summer program for teachers. So there would be 1 week where a teacher from a school would go somewhere and interlink with the environmental organizations that are available in San Mateo County. And we wanted to see if that had an impact on the connectivity of the school that teacher belonged to. So this Kumu visualization shows the network for the school year 2017-2018, where the triangles are schools and the circles are environmental education organizations. The black triangles are schools that had a teacher that participated in ESTF. And you can clearly see that a teacher that participated in this program, or a school with a teacher that participated in this program, is way more likely to be integrated into this network of organizations and schools.
And now we'll go into the diversity of services. So earlier we looked at absolute access, which is whether the school is connected or not, but we can also look at access degree, which is a weighted measure. So that tells us how many connections the school has. So it's not just whether it's connected, but how many providers it's connected to. And we see here that the number of schools that are connected to ESC isn't changing significantly throughout the years of the program, even though the number of connections is varying quite a bit and it's appearing to increase. So we can say that there is more connectivity throughout the years.
Another aspect we look into is the access to different types of environmental education. Here we look at 3 types, which is environmental education, sustainability education, and natural conservation education. So we can notice that compared with the years 15-16 to 18-19, we could notice the pink region is getting significantly larger. The pink region refers to a school that has access to all 3 kinds of environmental education. Overall, the sum of red, purple, brown, pink region, which means a school has access to more than 1 kind of environmental education, also gets larger, which means schools are getting more diverse environmental education. So talk about the impact is that we find out how the regional eco-literacy units can affect the access and diversity of environmental education in public schools. So environmental education policy lack of empirical evidence, and we hope to use evidence to inform and support a more regionally adapted policy. We will present our findings to San Mateo Office of Education in June. For future analysis, we'll repeat similar analysis in counties with different characteristics. That's the end of our presentation. Thank you.
Awesome. Thanks so much, guys. It's great that you're able to present this work in June as well. We're going to move on to the next team, Voice of Specially Abled People, and their work on sentiment analysis on disability, which is a comparative study between the US and India. Are you guys ready to share?
Hi. Yes, I think everyone is here. So
Awesome. Go ahead then and get started.
all right. Hello, everyone, and welcome to our presentation. For VOSAP, which stands for Voice of Specially Abled People, we aim to identify the hardships and gaps between those with disabilities and those without, and seek to find solutions for these issues. So this semester, we have an amazing team of interns led by me, Iris, the project manager, and Pranav, the founder of VOSAP. So our research focus, we changed a little bit throughout the course of the semester, but we basically will be looking at the sentiment of social media from both the government and social media perspective, because we think it will give like a holistic review of how disability is perceived in the society, right? So I'm just gonna like have my interns lead you guys through the entire research workflow shown here on the slides. And we will start with social media analysis, starting with Reddit. Sophia, you can start.
Oh, great, thank you. So the objectives for the Reddit sentiment analysis, I think it's lagging a bit for me. Sorry, so the objectives I had for the Reddit data analysis were to web scrape different subreddits for different disabilities. I wanted to do ADHD, amputee, blind, deaf, depression, disability, and dyslexia. Then I applied the Vader model to quantify the sentiment for each of those Reddit posts and compare the ratio of positive and negative posts between different disabilities. And then lastly, I combined all the data sets to see if there was a relationship between popularity and sentiment. So when it came to classifying the post, I used the Vader model, which assigns a vector value to each word in the post and an overall score ranging from -1 being the most negative to +1 being the most positive and 0 being neutral. When we look at comparing the sentiment over different disability subreddits, we can see that the ratio greatly differed between different disabilities. Disabilities like blind and deaf had a very large positive to negative ratio, whereas depression had a very large negative to positive ratio, which is not surprising given the nature of depression. I also looked at the actual vector values, and this kind of shows how some of them have more neutral posts like dyslexia, where some of them are more extreme like depression. Then lastly, I combined all the posts together and looked at the popularity, which I quantified by using Reddit's score. The score is the number of upvotes minus the number of downvotes. And as you can see, as the posts get more popular, there is a general positive trend towards more positive posts being more popular. And this could be just the way that we measured it by using score, which is people may be more likely to upvote posts that are positive. I'm going to pass it off to Helen to do Twitter data analysis.
Thanks, Sophia. So the next slide shows the objectives for the Twitter data analysis. The different tweets were scraped in 2 different ways. So the first kind of way is by timeline. So 500 tweets per year from 2014 through 2021 of tweets that would come up if you look up disability. And another way we look for tweets was using disability related keywords and finding a bunch of tweets relating to that. This is because we perform 2 different types of sentiment analysis, one regarding with time and the level of sentiment changing throughout the years, and second being sentiment compared to like the popularity of posts. Instead of Vader, we used Flare, which uses subword embeddings to measure sentiments. So moving on to the next slide, this is like overall sentiment over time. One thing to note is that the red line shows a neutral sentiment, and starting 2019, sorry about the background noise. Starting 2019, there shows a significant dip down to negative sentiment, which is likely resulting from COVID because of the disabilities that may have arisen from COVID or people needing to file for disability insurance. Next, this is more of a deeper dive on the previous graph showing the different counts of actual positive and negative tweets. Kind of shifting gears to the popularity analysis, we have violin plots showing the distributions of sentiments based on different categories that are like 25th percentile up to the 75th percentile. One thing to note here is that in the high category, there are the most number of positive outliers compared to any other category. And now I'll pass it off to Matthew to talk more about government sentiments.
Can you guys hear me?
Cool. Yeah, so after collecting the Twitter data that Helen mentioned, we decided to look at politicians' tweets. We have data from 23 politicians. And what we noticed initially, Iris, if you want to switch on to the next slide, is that out of the 60,000 tweets we collected, only 150 of those even pertain to disability in any way, shape, or form. So we decided to do a topical analysis to see if politicians were tweeting about everything with the same rates that they were of disability, or if there was a particular care to other issues, more so than disability. So the way we did this was through the latent zero share allocation model that you can see below. Basically, we get our data set of tweets, we clean it, removing stop words like to, the, and of, and emojis, just getting words that have actual meaning. We choose a parameter or a number of concentration or topics that we want to get. And after a little bit of work in Jupyter Notebook, we have generated 15 topics that each have 4 words that are jointly put together that you can see on the very left. So the model itself only spits out the 4 words, and the interpretation is my own and the groups as well. That when we see something like Obamacare, we're probably seeing topics like Obama, health, medicine, and care tied together. And if we go into the next slide, I can talk about some of the implications from the graph. The model ended up describing that there wasn't a topic that had such a low propensity, like 150 words, implying that there is definitely definitely less attention to disability matters amongst politicians. And the way we can see that is because if it would have been worthwhile to expand over 15 topics if there was some sort of uniformity over the 15 topics, like if they all had 4,000 tweets. But since some of them had well over 10,000, then we took note that there wouldn't be that sort of distribution. And now Sarah will go in and talk about governmental analysis with legislature.
Yeah, thank you, Matthew. So we also wanted to analyze whether there was any legal bias towards people in the disability community. So we collected governmental documents pertaining to laws and policies concerning people with disabilities and analyzed them in order to visualize whether government data contained positive, neutral, or negative sentiments towards the community. Once these documents were collected, we extracted the text utilizing the PDF Plumber package and created a word count of the sentiment words we chose pertaining to the disability community. The sentiment words we selected were manually labeled as positive, neutral, or negative based on the official definitions gathered from disability language guides. After obtaining the word counts, we joined the data into one master data table with the word counts across all the documents and then visualized them. So the first visualization we created was of the top 10 most frequently used words. And the second visualization we created was of the frequency of sentiment ratings across all the documents. And so we can observe here that the neutral sentiment words were most prevalent, followed by negative then positive sentiment words. The two associations that can be made with these visualizations is that first, positive sentiments were least frequent across the data, and that second, the neutral sentiments were most frequent. Both of these associations show us that those who draft these legal documents are not necessarily educated about the most up-to-date terminology pertaining to the disability community. And in addition, we also visualize the top 10 most frequently used words as well as the frequency of sentiment ratings per document. So as an example, here are 2 visualizations pertaining to the Title II ADA Act, which requires that the state and local government give people with disabilities an equal opportunity to benefit from all their programs, services, and activities. Here we can observe a similar trend as stated earlier, where the neutral sentiment rating prevailed with the highest frequency.
Right, and finally, there are some limitations and improvements. Basically, for example, for the politician tweets, there simply isn't enough tweets, and that's why we perform topical modeling instead of like any sort of like sentiment analysis or trend analysis. And there are some other factors that can be considered. For example, we can try to contextualize the perspective of the speaker, and we believe that if you try to contextualize the speaker and see if they're actually a person with disabilities themselves, or if they're speaking from like outside the disabled community commenting on sort of that kind of issue, it would have like more meaningful conclusions out of it. And so that's the end of our presentation. If you're interested in VOSAP, you can check out these links below. And that's a wrap for our presentation. Thank you so much.
Thank you guys, really interesting work. Let's move on to the next presentation. This is from the UC Berkeley's Seismological Laboratory. and their project and work towards machine learning-based detection of micro-earthquakes near UC Berkeley campus. And this is our second to last presentation of the day, so we'll have one more after this.
Right, so I'll just go ahead and share screen.
Awesome, yeah, go ahead.
Okay, hello everyone. My name is Ecoliteracy. Thanks for sticking around to the near end here. I will be presenting our project for the data science discovery team here. Our project's name is Machine Learning Based Detection of Micro-Earthquakes near UC Berkeley. So let's go ahead and get into it. So motivation. So micro-earthquakes are a common occurrence in California, particularly in Berkeley. Being able to detect them is a critical task for the safety of everyone. However, being able to accurately read a seismograph is a time-consuming task that requires a skilled seismologist. So that's a clear problem that we're trying to alleviate. Now let's get into the actual background. So I've prepared, or I've not prepared, but I found a short video that explains a little bit about the particular waves that we're concerned about with micro-earthquakes. So let's take a listen if you guys can. Can you guys hear that?
I don't think we can. Usually you'd have to share your audio as well.
Okay, no problem. I'll just go and explain it. So the main takeaway from that video was that for earthquakes in general, specifically micro-earthquakes, but there's two types of waves we're looking for, and they're called primary and secondary waves. And the main takeaway is that primary waves are fast and they propagate parallel direction of particle motion or the energy motion, and S waves are slower and they move transverse. So P primary fast, C S secondary slow. That's the main takeaway from that video. Okay, so let's talk about micro-earthquakes in particular and their noise. So if you see this red line right here, that is the Hayward fault line, and it goes right through Memorial Stadium. So that's kind of important for us. So micro-earthquakes are generally to be understood to be a low intensity earthquake with about 2.0 on the magnitude on the Richter scale. And the reason we're so concerned about it here at UC Berkeley is because, like I just pointed out, this is the Hayward fault line. And because we're concerned about it is because there's a lot of micro earthquakes that happen towards the fault lines because of tectonic shift, like moving, right? So micro earthquakes are going to be a common occurrence in UC Berkeley, particularly around this northern or eastern part of the campus. So they're all, but however, because they're also slow or low in magnitude, they're also prone to noise environments, such as like sporting events, construction, and heavy vehicles. So our seismometer devices have trouble sometimes discerning what is what. So our project mostly revolves around trying to pick out those two things. So let's go ahead and talk about the data themselves. So our data is typical time series data, where the y-axis is the magnitude of an earthquake in a particular direction. So if we can see right here, this is the one that we were mostly working with in our research and the one I'll be talking about in our in this presentation. So this is station 1073. This is in the Z direction, so in and out shear, north, north, south, east, east, west. So just typical time series data that we're going to be looking at, and with the y-axis again the magnitude, and if we switch them all together, it makes one earthquake, as we'll see. Okay, so goals. So our goals are to employ 3 popular seismic machine learning models to detect micro-earthquakes near UC Berkeley campus, and we're doing that mostly with the help of these 2 APIs, which are pretty critical in the seismology world for Python. Then we want to detect the phases between the primary and secondary waves, so the phase of the time interval in between those P and S waves, and then finally we want to classify the noise and seismic waves in the time series data. So let's get a lay of the land first and see where everything is. So here's a map of our detection devices, and blue crosses. You see they're dotted all around the Berkeley area, and the red crosses with the black boxes or the boxes are the earthquakes themselves. So let's get a zoomed in picture. So here's UC Berkeley campus. As I just pointed out recently, that the Hayward fault line runs right through here. So with that in mind, the researcher, he put a bunch of seismic devices right around the football stadium in hopes of getting one. And luckily we did. This one right here, which I call the Strawberry Creek earthquake, is right up against there. And that's the one that we're going to be concerned with throughout this presentation. So the way we determine which seismic devices we want to do or use is that we basically just created a function that returned the n number of shortest distance devices from any given earthquake. We just use the Euclidean distance. So here's pretty much code explaining that. So we wanted the 4 closest ones, and the way we determined which seismic device we work with, 1073, is the 3rd closest. So models, the API that I talked about, they offered 3 models we use. We're short on time, so I'll just breeze through this and let's go to the results of these models. So here's our time series data, all 3 earthquakes that are smushed together, and they look like this. And here's a legend telling us which direction they're in. So we can kind of see, even if you don't have a seismic background, that there's probably an earthquake here, but definitely not earthquakes of high probability everywhere else. So these models perform really poorly. However, this model in particular performed okay. It was able to detect an earthquake here, but it didn't think there was one anywhere else here. And here's an attempt of cleaning up the actual earthquake data itself, where we just tried to like use the most important features and like nothing else, but it performed even worse. So that led us to the motivation of clustering. It's actually a technique I think the BART group used as well. We basically needed to make an autoencoder with the clustering algorithm at its bottleneck. So it's a little different how they use it. They use it, I guess, how for NLP, we're using it for time series analysis. Kind of imaging is another use of this type of model. But right, so this is so we made it a deep autoencoder, a convolutional autoencoder. Here's the architecture. Oh, I should cite my source for them. This is the paper that we really use a lot of motivation on our autoencoder for. But right, here's the general architecture, and here's a TensorFlow like summary of the layers. And let's go ahead and skip to the results of this architecture or this autoencoder. Right, so the problem was none of our like data is labeled, so we don't really know if there's an actual earthquake or not here. So the main inspiration of using an autoencoder is that this unlabeled time series data, and we need a way to cluster the noise and the actual like events of the PNS waves. And luckily, our autoencoder, our deep autoencoder, worked really well. So we were pretty excited about that. So here's like all like the noise, obviously, right? So we just take a look at it. Here's clearly not any like earthquakes here. So this is the cluster that it first created that it believes is just like junk. We don't need it. And here's the cluster where it believes is the actual like event. So that was great. It worked really well there. This is an experimentation that we were trying to like play around with the number of clusters. Perhaps it would include or improve the ability of picking out in that phase that we're really concerned with, like right this time interval here. But it didn't. So we're like going forward, we really want to try and tune into the amount of clusters that are optimal, but it still remained really, really good at separating the noise, which is really promising. Yeah, so in summary, because of UC Berkeley's proximity to the Hayward fault line, micro earthquakes are always going to remain a common occurrence, and the ability to quickly and accurately detect them was always going to have impactful implications for not only our campus, but the whole world. The flagship machine learning models that the researchers used, they did really bad, but the most promising approach that we use for unlabeled seismic data is the clustering method. As shown, a convolutional autoencoder does well to isolate the PNS waves and the noise, and we think that we could further improve it by tuning the K and clustering algorithm at the bottleneck. And that's our presentation. Thanks for sticking by.
Awesome. Thanks so much. The next and final project of the day is, I think it's a collaboration between the Arctic Ice Project and Climate Informatics, actually, evaluation of climate modeling to determine theoretical effective area for a potential surface albedo modification. Are you guys ready to share?
Yeah.
Awesome. Go ahead and get started then.
All right. So yeah, thank you everyone for coming out today. We are the project with the title Evaluation of Climate Modeling to Determine Theoretical Effective Area for Potential Surface Albedo Modification. It's a collaboration between Climate Informatics and Arctic Ice Project. My name is Srikar.
My name is Joe.
And my name is Chingi.
And with the help of our wonderful mentors, Dr. Delina, Dr. Savarna, and Dr. Leslie Field, some of whom are on the call today, we'll be going through what we've accomplished over the course of the semester. So essentially, the motivation behind our entire project is the amount of sea ice that's present in the Arctic oceans is rapidly decreasing due to climate change and global warming. And in an attempt to actually restore the volume of sea ice that's actually present, the Arctic Ice Project, led by Dr. Leslie Field, was able to develop a method, a technology to actually enhance the amount of sea ice that is present and improve that. And so it involved using non-toxic hollow glass microspheres, which essentially when when like a layer is put on the sea ice, it helps regenerate the sea ice and like essentially restore it. As we can see in this picture on the left, we have a small scale field test actually done, and the amount of sea ice that was present versus like a control without the actual modification treatment, there was more using this actual technology. And on the right, we have some plots which basically show how the volume of sea ice might be present if there is no modification. So that's the one on the left, like the business as usual. Whereas if this modification technology is actually used, we see that there's a lot more sea ice cover. And so these are just models that we have created to show, what the potential might be. This is after the whole vetting process. And so we've essentially determined that this is a technology that would be useful for actually restoring the sea ice. And over the course of our project, our primary goals were essentially to evaluate the sea ice cover. This, it depends on several features such as the thickness, area, volume, the ratio of the newer to the older ice. How sensitive are they to this surface albedo modification enhancement that we're doing? And we really want to figure that out so we can figure out where exactly we can apply this technology, where what's the optimal location and time for actually deploying the technology so it'll have the largest impact. In addition, we also want to investigate how sensitive the sea ice albedo is to the cloud cover, the clouds in the area. So that includes how cloudy it is, and also the cloud fraction at different vertical levels, if it's low, mid, or high. And so that's another thing that we were really interested in seeing over the course of our project.
So here are all literatures we have read for climate modeling, which fit our albedo data. And for the next slide, we have extracted some models from those articles and these models, and we have already implemented linear regression. Since sea ice thickness is a very important variable in our dataset, we plan to use decision tree and random forest to estimate it. Lastly, we plan to use gap filling models to fill out missing data, which used gradient boosting based albedo estimates outperform alternative estimates. And Joe is going to talk more about our implemented models.
Yeah, so in terms of our data and the models, first of all, using the high performance cloud computing systems provided by Seismological, we were able to look at the data from the CSM climate model output. And in particular, we focused on two cases, control and global. So initialized from different phases of the Arctic oscillation. So there is positive, negative, and neutral phases. The variables we're particularly interested in is HI, so the sea ice thickness, and AICE, so the sea ice concentration. And we're wondering, so the question is how changing to albedo will, how the changes will be reflected on these two variables. And the format is a very common grid data in geoscience called NetCDF. And initially we were able to read and visualize it on the cloud by loading a NetCDF module. But as we worked and research more on this data, we discovered a Python package called Xarray, which some of you might be familiar with. It's essentially Xarray introduces labels in the form of dimensions, coordinates, and attributes on top of NumPy, multi-dimensional arrays. So we found out that this enables a more intuitive and concise representation and also manipulation of the data. So that's what we went for. You can see that on the right. So next, what we did with the data was that we extracted using NCO operators on the cloud. So we extracted monthly variables concatenated with the years 2001 to 2080. And we selected the Arctic region in particular. So we tried plotting the results especially between the control and the global cases. So these are the differences between the control and global cases. We plot them using the NCR scripts, which is a NCR command language. But then in the right, you can also see, we also found out that we could plot X-rays pretty easily using some built-in methods supported by Matplotlib. But we ended up not using them because we wanted the format to be consistent with some of the previous results generated by the group. But essentially the takeaway from these graphs is that for both the sea ice thickness and the sea ice concentration, you see that the difference, which is after control, there's a slight increase for both, especially for sea ice thickness. There's an overall increase, whereas in the sea ice concentration case, in general, there's still an increase in the concentrations after we control. So this is the key takeaway from the graph. Can go to the next. So about our basic linear regression model. So as mentioned, our model was to try to see how the sea ice thickness and the concentration would change as we change the albedo of the ice and snow. And then, so we started with a simple model, which has stochastic gradient descent as optimization. So we tested our model initially on simple data and it works pretty well. And Currently, we're in the progress of finalizing our model in the sense that we could modify it to adapt to this new technology of X-ray data sets in the future. And yeah, there are like certain difficulties, of course, as we work in the cloud, such as setting up the correct working environments and adopting all these new technologies. But overall, we're still very happy with our progress, and I will hand over to Srikar and Sheen to discuss what we expect future work to be like for our group.
And our next step is going to continue testing models and using NASA observations to get validation.
And yeah, going off of that, like we built out the linear regression model. Another like way that we want to proceed was using decision trees as well as multiple decision trees in a random forest, as well as using further optimization algorithms past the ones that we've already used. And with that, that wraps up the work for this semester. Thank you all for listening.
Awesome, guys. I'm really happy with the presentations this semester. I think everyone has done excellent work, especially, even the teams that we didn't, unfortunately couldn't highlight today. I wish we could have spent more time on all of the presentations, but so much great work this semester. I have the fortune of announcing the award winners. Well, before I do that, I just wanted to say that, this semester was really competitive, and we had many great submissions and great projects. So we had a really hard time judging this, but without further ado, I'll go ahead and announce some of our winners. The first award that I'll announce is the Data Visualization Award. This is an award that recognizes the team with the best data visualization. Data visualization is something we really value in data science. It's a key method to convey information for non-experts and gather more attention and create a larger impact. And the winner of this award this year was Regional Scale 3D Ground Motion Simulations of Moderate Earthquakes on the Hayward Fault, which was the Seismological lab that presented second to last. So if we could all give them like a round of applause. Maybe even with you clap the emoji or your hands, whatever. And this project findings really showed impressive and impactful visualizations. So I'm really excited for that team. We did have a runner-up for this team, which was expanding the Axos Insights program, the Catalyst Off-Grid Advisors team. Also excellent and impressive visualization techniques based on good analysis. So awesome work, guys. The next one is the Team Collaboration Award, which recognizes a team that has persevered and overcome data science related challenges with their project and succeeded in creating and building a strong scaffolding with a promising project outcome that will have a meaningful impact. The winner for the Team Collaboration Award this semester was Sentiment Analysis on Disability under Different Social Contexts, which is the VOSAF team. And this team successfully took ownership of the project and provided structure to a challenging research question. So really excited for VOSAF there. The runner-up for this Team Collaboration Award was Evaluation of Climate Modeling to Determine Theoretical Effective Area for Potential Surface Albedo Modification, which was the team that actually just presented the Arctic Ice Project collaboration with Climate Informatics. This team integrated seamlessly with each other and showed initiative. So that's really exciting. Next up, we have the Data Science Insights Award. We recognize a team that has bulletproof insights based on their methods. What we defined as an insight was anything that increases or improves the understanding of a trend, system, or phenomenon and how this arises. The winner for that award, the Data Science Insights Award this semester, was the project Application for Data Science for a Localized Climate Prediction product, which was also a climate informatics project. And this project explored various models for climate prediction and conducts interviews with solar utility providers to understand the findings deeply, which is really great. The runner-up for this was Tackling Mass Incarceration through AB 2942, Expediting Case Review Summary for Criminal Case Resentencing, was the People Lab. That study applied data science to increase the understanding of disparities in mass incarceration, which we recognize, really key data science insights for social good. Finally, the last award that we considered this semester was the Azure Cloud Computing Application Award. And this award recognizes the team with the best Azure application. So cloud computing, as everyone here knows, is becoming increasingly popular nowadays due to its high flexibility, low cost, and many other great features. And the winner for the Azure Cloud Computing Application Award was Project AIE, which was Core Tech. And this team successfully applies cloud computing integration into their model and application deployment. Like I said, it was really competitive this semester, and we have a ton of great teams, the biggest semester ever, I think. And I'm so grateful to have had the opportunity to work with so many of you. And I look forward to seeing hopefully many of you in the future for future projects with our students. That concludes my portion. Anthony, I'm going to hand it over to you for closing remarks.
Well, first of all, I want to thank you, Alex, for all the great work you've been doing this semester and especially shepherding this wonderful showcase. So applause to you for all the hard work. And also all the other graduate fellows and the coordinators, student coordinators in our program. Really appreciate everybody's effort. Thank you for being here for the last 2 hours almost. And it's been a whirlwind ride over in many domain areas. And we'll hope to see you again in the coming semesters. And we have a lot of interesting ideas. And if you have ideas for projects, let us know. We'll have an application open up soon for research projects. And hundreds of more students will be part of this program in the fall also. So yeah, that's a wrap. Thanks again for coming. And if you have any questions, feel free to email us. And we look forward to the next semester. All right. Take care, everyone.